So we have a fun little example here of a train collision. It's a head-on collision, but that doesn't necessarily mean they're coming one head to the other head. This is actually coming up from behind. It's a rear-end collision, if you will. But head-on just means in one direction. So this is actually a very, very useful um, example, which you can go back to a number of times. And it breaks up into two situations. The first situation is going to be inelastic, where they stick together. So you had couplings here, for instance, and the other situation would be elastic. Whoops. Elastic, where you can just imagine there's springs between them or something, bouncing off of each other. One spring on one. Basically, they could be rubberized, if you will. These are very low masses, so they're not really train cars, they're lab cars, but it's the same idea. Lab cars tend to either have magnets or Velcro, or if you're really low-tech, tape. I've done that a number of times to make them inelastic, and then elastic is usually a spring or magnets in the opposite direction. Works either way. And so, what is the total momentum going to be before the collision? So remember, this is before the collision. This is a picture of that. Total momentum is going to be the momentum of the first car plus the momentum of the second car. Well, don't forget, here we go. Momentum is mass times velocity. So for the first one, its mass is 2, the velocity is 4, so it's 8 kilogram meters per second. And then 5 times 2 is 10 kilogram meters per second. So the total momentum is 18. So that doesn't change. That is boring. It stays the same. And so the question, here, I'll even write it in here, 18. The question is, what is the total momentum going to be after the collision? It's actually a trivial question, because since total momentum is boring, it doesn't change. It's going to stay the same. So parts C and D are really where we branch off. So let's just take two different scenarios. So in part C, they couple together, and in part D, they bounce apart. It's two completely different situations. So what's the speed of the combination going to be after the collision? So, whoops. Here are the cars. One car, another car, and they're actually going to be together. All right. Imagine that they were about the same there. In fact, I'll do it this way, since we already perceive a greater mass to imagine like it's a size. So. Oh, I can do it. Love it. Learn something new every day. Okay. Oh, you can even clone things right there. Okay, so anyway, they become one. I'll pretend I welded them together. It happens. So they're hooked together. So the new mass is 2 plus 5, because here's the 2, here's the 5, right? Or 7 kilograms. That sounds very familiar, doesn't it? Very, very close to what you've seen in the PowerPoint with the balls. Now the question is, what's the new speed going to be? Well, again, take this idea, momentum is mass times velocity, cover up the velocity, it's going to be momentum divided by mass. And the momentum was 18. And we know that because it's both of them together, the total momentum has to stay the same. divided by 7, which is the combined mass because they're stuck together. 18 over 7, it's not going to be a simple number. 2.57. Okay. Meters per second. So that's how fast they're going to go if they had stuck together. And it happens to be positive, so it's to the right. And that makes sense because the momentum was to the right. Now let's change the situation entirely. And let's say that they're now going to bounce apart from each other. They can be bouncing in the same direction, right? This one could continue on going slower and this one faster. Or they could be bouncing back. If total momentum was 0, they would just cancel each other out. They'd be bouncing away at positive and negative. But in this case, we don't really know. But we did know that the target car, which this is the target, has a velocity afterwards of 3 meters per second. So here's the situation, and I won't be fancy with shapes this time. The new velocity, 3 meters per second. We don't know what this one is. We do remember the mass. That was 2 here. The mass of this one is 5. You can get really fancy and you can put little 1s and 2s there if you wish. But the concept's the same. So which direction is this thing going? That way, that way? We don't know. We got to find out the velocity. If it's negative, it's going to the left. Positive, going to the right. So again, total momentum is boring. Let's find the momentum of this object. Momentum 2. 5 times 3, it's 15 kilogram meters per second. Well, that leaves 3 kilograms meters per second as the momentum for this one. So this object, this first ball, or sorry, this first car, is still moving to the right, but at a much slower pace. And what is that pace? It's easy once you get to a point to think that you finished a problem, but we haven't. Since we found the momentum of this ball, again, this follows exactly basically the notes that I've given before. We already found that one. The momentum, the velocity is going to be momentum over the mass, so it's 3. Velocity for the first, if you will, divided by the mass, 1.5 meters per second. You can see the kilograms cancel out. 1.5 meters per second, so we found that one. And that's just another really good example for you, if I do say so myself.